tenemos al profesor Markus Huddert. Markus es profesor en la Universidad de Aarhus, en Dinamarca, en la Facultad de Ingeniería Arquitectónica, de Arquitectura e Ingeniería. Trabaja con madera, sus temas de investigación, como veréis, están relacionados con fabricación digital, es decir, cómo hacer este tipo de construcciones en la realidad y cómo hacerlo en el ordenador. Y también veréis que parte de su investigación está muy relacionada con cómo tejer madera o cómo incorporar conceptos de tejer a las estructuras de madera. Y en realidad con estructuras a tamaño real, digamos, o sea, ya no hablando del material que tenemos aquí, sino material real de construcción. Whenever you want. Markus.
All right, thank you very much for the introduction and also for the invitation. This one is running?
Yeah.
Okay. So unfortunately, I don't really have any Spanish skills, so I can only offer German, English, basically these two options. So I think I will go for English. So yes. So so I mean, you can see in the title there's several topics, and I think all of them are relevant to some degree to you. Mainly the textile-inspired timber structures, but also nowadays it's really hard to work without digital design and fabrication. So we'll also try to talk about that a bit. So. And then shifting the focus a bit more towards the digital design and fabrication. And when I do that, I will try to do it in a way that we understand the importance of digital design and fabrication also in the context of sustainable construction. Just very briefly a few words about myself. So I'm originally from Germany, where I studied architecture, and I did a postgrad diploma at Städelschule in Frankfurt. I spent approximately 4 years in practice in Amsterdam for UN Studio and Power, and I then had the opportunity to start a PhD at in Switzerland on innovative timber constructions. I had a few postdoc appointments after that, and since 2019 I'm in Denmark. Some of my topics that I address in my work and in my research, in general, I think can be summarized as novel timber tectonics, so innovative timber structures, and working with or looking for innovative ways of working with timber in order to find more sustainable ways of building. So I'm interested in exploring and exploiting the properties of materials and also of assembly techniques. So this is maybe also relevant for you. You're working with textile techniques, textile principles. You're working with this maybe with a specific material as well. Interlaced structures or timber fabric, that is the biggest part I'm talking today about. Textile-inspired structures, digital design and fabrication, interlocking structures, and as you know, maybe since a few years we are becoming more aware of the sustainability issues that we have in building construction. So we have not only to think about how we build, but also how can we take buildings apart again, and how can we reuse materials, and how can we move towards circular construction. So in the very beginning, just very briefly, I want to address this topic of tectonics. And there's a number of important definitions. It goes back to Semper, and I think the one scholar who has brought this whole discussion back is Kenneth Frampton. It was a reaction to the postmodernist architecture. And then we have Edward Settler. We also have maybe here some definitions. The first one is in Danish, sorry for that, but it basically means it's from the Danish dictionary, and here in this dictionary, tectonics is defined as the art of combining elements into a whole in a system, as it is done, for example, in architecture or art. And Semper, when Semper talked about tectonics, he was talking about timber construction, and he defined it as the art of joining rigid linear elements into one stable system. So why do I bring this up here when we talk about textiles? It's also because of another other writings of Semper, where he actually studies different materials, and he also studies textiles. And actually, in his observations and in his definition, the knot, so it's a textile joint, right, between two ropes or between two yarns, that this can be seen as a prototypical joint in architecture itself. Or as it's written here, for Semper, the most significant basic tectonic element was the joint or the knot. So there is some history in textiles that is relevant for architecture. And tectonics is also about how the way we build the materials, the construction methods, how they can have an impact on how the building looks like, or how they are shaping the building. And here maybe we're moving a bit closer to timber construction. And I would like to explain that with the example of timber construction. So traditional timber structures, they are made of linear elements, as you can see here. So they're directly derived from the tree. That's why they look like this, right? And how does the geometry or the properties of this element influence timber architecture? Here are some examples on that effect. So how can we organize these elements to make a building? We can layer them horizontally, like you can see on the bottom left. We can have vertical arrays or horizontal arrays, and we can organize them in spatial organizations. And when I started my PhD, what was interesting for me was to see what is the impact of more contemporary timber elements and large panels like CLT, maybe you're familiar with that, or also LVL. These are still relatively new products, and the question was then, or one of the questions was for me, how a change from the linear element to a panel element can have an impact in the tectonic quality or in the architectural expression of buildings. Another thing was how to use specific material properties. And if we look at timber, on the left you can see a contemporary example. I think it's a CLT building. I think it's good and important that we're building now more with timber. But also what we see here is that it's a bit like imitating buildings that use other materials. So I was interested in the special property of timber for elastic deformation. And you can see on the right-hand side an example of the flexibility of these large panels. Then the other aspect or inspiration for my work was textile structures, because also in textiles, actually the formability of the basic elements is actually a requirement to produce these textile structures. So I started with, in the beginning, with trying to get a better understanding of the different techniques and different ways of classifying textile techniques. And this is a bit of a short summary that you can see here. So we have simple fiber assemblies that can be felt, for example, or yarn, where we basically have an interaction of threads. And then we have more advanced fiber assemblies where the threads are used in more complex structures, and there we have, for example, knitting, braiding, and also weaving. And maybe one more thing that was relevant for me about textiles is that textile structures also have properties that could be relevant for buildings. And this is maybe especially also the case in woven structures, as we can see it here. So in these textiles we have something that we can call a system effect. So we have many elements that interact, that are woven together. So we have some kind of redundancy, which means if one of these elements fails, we still have the neighboring ones that can take on the loads and keep the structure from collapsing. And another thing that is interesting in woven fabrics, but also in other fabrics, is a kind of a modularity. So there's actually a unit cell that is repeated in the whole structure. And as you can see in these examples here, you can create different patterns. You can configure different structures by changing or using this module in different ways. And it's very simple. It's basically just two threads crossing like that here in the example of the woven structures. Yeah, so I looked at all these different principles and techniques, and then I tried to transfer some of these principles to a larger scale and also to strip shaped timber panels. And yeah, I was very much interested in this modularity, and what I then tried here is basically using something similar to braiding with timber panels. So as you can see in these diagrams, the idea was that you take two strips of timber, you connect them like this in one point, and then you cross them here. And it's a generative approach where the geometry of the panels and the material properties and the assembly technique generate the form that you see on the bottom row. This is a very small scale model that is two strips of veneer or very thin plywood. And it's basically bringing the flat strips into a three-dimensional configuration. During these studies, I then managed, together with colleagues, partially to scale it up in our workshop to make a 12-meter long prototype of this module, this LVL. And this was part of an exhibition in a public space. So as you can imagine, if you put something in a public space, then you should test it before. So this is also something that we tried here. And it was quite fascinating to see. This was a different type of panels, but the principle is the same. That if you apply a vertical load in the middle of this structure, that the flexibility of the panels leads to these deformations, and it was almost impossible to get to failure. As I said in the beginning, today it's probably not possible anymore to build without working in a digital environment. So what you're doing here, I think, is very important, working with these physical models, because the physical model allows you to directly understand the material and it allows you to discover maybe some phenomenon. But then later on, if you want to exploit that, and if you want to maybe apply it to larger scale in building, then you also need to find a way to bring it into the digital realm. And here we simulated this process of form finding or form generation, also this finite element analysis with Markus, which also visualized some of the stress points in the structure. So you can see in the lower part here that where the two strips are touching, that there's a high compressive residual stress. Starting from this module, I continued to explore a kind of way towards a system. So how can you move from one single element to larger structures? And one way is to extend it by additional strips and then to produce these braided arches. This can also work in a convex concave way. And then systematically I moved towards more complex structures. So you can see in the middle, the starting point is the two strips to the module, to the arch, then having several arches next to each other. So the idea was here to have a system for load-bearing building envelopes. And then the last step was to move towards double layers. So having two layers of these arches on top of each other to create these envelopes. And that was one of these initial prototypes of that system, where you can see on the interior 3 arches and then 2 more on the outside. And the advantage of the double layer is that on the one hand you get a better structural performance, but also it improves the control over views, light, and maybe also ventilation. So I continued to study with some variations. This was actually a relatively small prototype, but then the scale went up, and this one was about 6 meter span and a 3 meter height in the middle. And what you can also see here is that the outer layer is a bit rotated, and the motivation for that was to stabilize or brace the structure in one direction. And this is the view from the inside. Yes, so there were a number of exhibitions also of this work in the City Hall of Lausanne. Then the exhibition that I showed at the beginning, and also it's already some years ago now in the Expo Shanghai in the Swiss Pavilion. And also a number of publications also from other authors that are covering that work. Do you have any questions so far? No? So, what I'm trying to do in my work is to find a connection between the research and also the teaching. So, similar ideas or principles were also used in our design studio. And here, this is the studio from EPFL with Rainer. And here it was a bit of a challenging task, because the task was to work with textile structures as inspiration, and then to design a lookout tower for one of the big summer festivals in Switzerland. Why do you think that could be challenging to have textile principles used in a tower, maybe from a structural point of view? So textiles typically they work on tension, right? So I can do this, but then if I do this, it doesn't work on compression. So there needs to be some kind of translation of these principles. A change in material can be one part of it. But that was one of the challenges, and I'm just maybe showing here some of the outcomes. Where here we have kind of a wrapped layered structure, but also using the Zollinger principle, which is basically working with shorter elements that connect like that and can form a grid. So one challenge when you scale up textiles is the scale of the basic elements, right? Because in textiles we have almost the yarn can be of any kind of length. If we move to buildings, we have to start thinking at one moment about discrete elements, about parts that can only have a certain length. So this continuity that we have in textiles cannot be fully achieved or very hardly achieved in buildings. So this, what you see here, is one solution of that. It looks like continuous elements, but actually it's broken up into shorter elements. This one is another example, and it's a bit more, let's say, a more abstract interpretation of textiles. And it's based on the logic of reciprocal structures. So, who has heard of reciprocal structures? Everybody? Yeah. You know this trick when you have a bowl and you have 3 knives, and then you cross them in the middle, and then they hold. So that's one example, and then there's of course the Da Vinci Bridge and other examples. So here, this student had the idea to translate the textile into this reciprocal system, and then pile these reciprocal rings into a tower. Here, this is not a tower design, but this was more like a pre-study. So what we tried to do back then was to start on a smaller scale and then move to a medium scale and then to the building scale. So there was also something like a furniture scale, so to speak, in between. And I think this example here was quite interesting. It uses a technique similar to weaving. And in weaving you have 2 systems. You have this system and this system, so 2 directions. And here, these 2 systems are overlapped and then fixed. And then they're bent in the other direction and fixed again. And that's how basically you can, the image that you see on the lower part is maybe easier to understand. So this is a way of creating these kind of spatial pockets. And the lower image shows a smaller scale model, and then the upper one is actually almost as high as a human being. So we managed also to scale it up, and then the student proposed to use it as a kind of pavilion in a landscape where each of these pockets creates a kind of a private space. Another example from teaching is a workshop that I did in Innsbruck, in Austria. And there's also different approaches to that. So here we see something that is maybe more inspired from felt. So felt is fibers that are connected in a random, chaotic way. And here this randomness of the felt was combined with creating this kind of cylindrical structure. Here. And this was a another nice outcome of that workshop, where the starting point was a technique that is called connected looping. So we can see in the center of the structure we have a zone where the elements are interwoven, and then they go out, create a loop, and come back into the center, and that created basically this spatial structure where you also have an interesting interior space, and it could become some sort of pavilion. One challenge here is the loops. So the whole structure is resting on these loops, and if you scale it up, it becomes much heavier, and then the self-weight of the structure is holding it down or moving it down. So if you scale it up, it will also change a bit the shape of the structure. Yeah. So these are some more detailed photos of that. And what you can see here is that to keep the elements in place, we used rivets, these small metal elements to connect the wooden strips. A few years later, so that was in my time as a postdoc at Aalto University, we also had a workshop or a studio there which was about building skins, so building envelopes. And one of the students was interested also in studying textile principles. And here what we see is basically a variation of a woven structure, a woven pattern. And by using these strips, which have different material properties than textile yarn, applying this technique with this different material created this spatial pattern or spatial structure. He also studied principles of bifurcation, so starting with one solid veneer piece or piece of wood and then splitting it thinner and thinner, so it became from a solid piece of wood to a more woven structure. And then try to find out how combining woven elements into larger space-generating structures. So here you have three pieces that are based on the same principle, and by connecting them at the ends, you create this arched element. And well, yeah, he tried then to develop it further into, you could say, maybe an experimental building. It was not realized, but it's would probably also be challenging. But I think there's some ideas here that are quite interesting, and also, of course, the question: if you have a structure like that, how do you close it really? How do you make it weatherproof? These are also important questions, and here the idea was to have some membrane, so another type of textile, and in that sense I think it's interesting to have this convergence of scales where you have a macro textile pattern and then other textile structures that are creating the building envelope. So I think that was the main part on textile-inspired structures. And I think what is interesting also in textiles is that you could say that textile technology and the automation in textile technology was also a key step towards the development of computers. So in the Industrial Revolution, there was the invention of the Shakar loom, and it's basically automating the production of textiles with punched cards, right? So basically, you make punch cards, a pattern, and you program the textile that you want to produce. So this is kind of the transition now to the second part, where maybe I will try to talk a bit more also about digital fabrication. But it's a bit of a transition. So this project or these studies here, they are still to some degree related, or that it was a parallel study to the ones that I showed you before. And this was a question: how can you abstract, or how can you introduce a step of abstraction in woven structures? And the basic idea is illustrated on top. So you have this woven pattern, and as I said before, you have two directions in woven patterns. And can you still do something similar if you take away one of these? And the solution could be what you see here is that you have slots in these strips, and then you basically interlock them or slide them together. So yeah, this is also something I think I mentioned in my research topics. It's these interlocking structures, which also found some interest in one student who made a small model that we then developed further into a pavilion. So it's an interlocking timber structure, and this one is required also digital design and fabrication because we have a three-dimensional shape, and we needed to produce slightly more complex joints. So these interlocking structures, they work with panels that have a slot, and then you slide them together. And this is also, or could be, relevant for disassembly, right? Because it's a relatively simple connection, and potentially it could be taken apart again, and the elements could be used again. So what we have here is a modular structure, and these cuts that you can see here, they are angled. So you cannot cut it with a normal tool, so you need to have a 5-axis mill. And this was then the result of that study, where we had I think 7 meter span pavilion based on one unit. And yeah, that was maybe one of the first examples of these interlocking structures. As you can see here, the interlocking elements, they follow one surface, right? We have this arch, and the elements follow that arch. So also then back in Alto a few years ago, I was wondering, could there also be a solution of bringing this interlocking into a spatial dimension? And I studied in a simple manner in the computer some transformations, moving from an orthogonal grid to an angled grid, and not thinking only in the dimension of the surface, but in the dimension of space. And there I also had the first time the possibility to work with a robotic arm and robotic milling. So this was a small-scale prototype. Each of these elements is approximately 30 by 30 centimeters. And the reason for that is also some of the limitations of the production facility, which was this robotic arm that you can see here. And one thing that is always important when you use robots is safety. So we needed to make a kind of plexiglass cave around it, so that if the milling bit breaks, that it's not becoming a projectile and hurting anybody. And because of that, the production space was a bit limited. But then the idea was still to bring it up to another scale, and also looking into the structural properties of that. And it's quite interesting. These connections, they're working like a lever arm. So in this direction they work pretty well. And in this design here, you can see that it's basically like a loop. So in this configuration, this principle worked pretty well, and we then made a larger demonstrator that was also part of an exhibition at Art University. And here we had to use a 5-axis mill because the working space of the robot is not. We have one basic element, maybe you can see it in the bottom left. It's a kind of X-shaped plywood piece. And it has these 4 legs with an interlocking connection. And you can see in these studies that it can be combined or integrated in different modules. So you can have a triangular shape, you can have a pentagon shape, or a square shape, and then these can be combined into larger structures again. And yeah, so in the final pavilion you can see these X-shaped elements that were approximately A3, so that's 40 by 30 centimeters. And they were produced with laser cutting. Yeah, here are some more examples. That was also a prototype for a student for this studio that I showed earlier, the building envelope design studio. And here I helped the student and produced the elements for this prototype with robotic milling. The student then continued and worked then more with parametric tools, Grasshopper and Rhino. So she took up these principles and studied it further in her master's thesis. And this is one of the examples of what the system that she further developed could do. Another thing in this direction is a study that I did also at Aalto University. I call it the impossible question mark roof. And as you can see, it's again this principle of interlocking panels to create a shelter roof for an experimental concrete wall. It's also interesting. Normally, you wouldn't think that a concrete wall needs protection, but in this case, it was like that. The problem was here. You can see that these elements have an angle in their connection. And we then did some experimental tests with colleagues in engineering at Aalto University. And this is also what I explained earlier. On the right-hand side, you can see that in this way, the connection works pretty well, but in rotation, it doesn't work very well. So that means, if you look again at this image, each connection is like a hinge. And if you apply a load, then it would start moving like that. So we couldn't build it back then, but actually you could add some elements to prevent this rotation, and then you could realize it. Okay, so the next slides are a bit more recent examples. So these are projects that I've been working on since I'm in Aarhus. We have a small team. The team has changed recently, but the projects I'm going to show are involving that team. So when I started there, I think after 1 year, I managed also to convince the department to buy robotic cobot, which means it's a collaborative robot. It's a small robot. It has a payload of 5 kilo. And cobot also means that they're more sensitive than the industrial robots, so they cannot really cause any harm. So that's, if you're working with several people and the students, then it's maybe the better option to work with such a robot to avoid any accidents. And one of the first studies here is related to what I've shown before, was the idea to look into building systems, to look into construction systems that have these interlocking connections, and that can be assembled with a robot in an automated manner, but also taken apart again. So a structural system or a construction system that can grow, that can shrink, that can change. And of course, these are very early studies and also on a small scale. So if you want to bring that then to a full building scale, of course, we have to think further, and there is certain implications of that. Yeah, we try to look into that and develop some options that could go closer to architectural solutions. And the whole studies are embedded in a kind of a framework. And I believe this is something that is already happening, is that we are using, or that we can use, and maybe we should use, digital tools, digital fabrication, automation to move to more sustainable buildings. So I think maybe 20 years ago or 10 years ago, mostly when people were thinking about digital fabrication and digital design, it was about exotic or complex shapes, complex structures. And of course this is fascinating, it still is fascinating. But maybe now we can also start thinking about how these tools, how robots, digital fabrication and so on, how computational workflows can help us in making building construction circular and reduce the environmental impact of buildings. One side aspect of that is also modular construction, so volumetric modular construction. So basically prefabricating boxes and then designing your building with these modules. And one advantage of this could be that such a building is easier to take apart again and to place somewhere else and to change. And in this illustration what we see is kind of two loops or two circles, and the first one is where you see different configurations of modules on different sides. And then the idea that maybe after 10, 15, 20 years there needs to be some modification. You can take out a module and automatically update it or change it and then bring it back into the other loop. And maybe I should add that what you see here is not meant literally as the way it would be built. So it's maybe more a conceptual diagram. Yeah, here's some more examples of the studies that I showed earlier with the interlocking, but then also some studies of how volumetric modules could be combined. Sometimes also in academia you can find the time to engage into architectural competitions, and that was the case, I don't know, when was it, 22 I think. There was so-called tree house competition in a botanical garden in London. We didn't win, but we tried to implement some of these ideas in this conceptual design. The next few slides are about this topic here, which is reducing construction waste. So maybe you are aware that building construction has a high carbon impact, but the building construction sector is also one of the biggest waste producers. And what is often happening is that the waste is either put into landfill or burned. So I believe that one way of also reducing the environmental impact is to take that waste and think about what could we build with it, could we reuse it for buildings. And yeah, so this is one study on that topic where we look into COT construction. So I don't know how familiar you are with COT construction, but you can see in the lower diagram that typically you start with these huge panels and then you cut out doors and windows. And these pieces that are cut out, that they are typically going to waste. So the idea here was to take these elements and find a workflow to bring them back into new structures, and also using the interlocking principle. Here you can see it a bit bigger. And we were working towards a pavilion that was to be shown at a conference in Aalborg. Aalborg is about 1 hour from Markus. So maybe the design that you can see here is, let's say, a bit experimental, but it's also meant to illustrate the potential of these circular principles and of upcycling. So the same could also work with more rational designs and with more rational patterns. This was the initial proposal, to have a pavilion like that with a bottom slab, a ceiling slab and a column in the back and the wall. And we had to rationalize it, and in the end we could build the front part that you can see here. And it was really nice because we could use the waste COT from a residential project in Denmark. So it was really the leftovers of an actual construction project that we could use here. So hopefully before the end of the month we will submit a research paper on that, and then it will also be the detailed computational workflow behind it will also become public. I think this is then maybe the final topic that I will talk about. It's related to hyperbolic paraboloids. Those are ruled surfaces. And what I found fascinating in these structures is that, yeah, they're double curved, they're complex, but they can be made from simple elements. So as you can see in this model here, and these are the outcomes of a course I taught 2 years or 3 years ago. You can build them from linear elements, from beam-like elements, and you can create these grids. And the other thing I was interested in here was to use such structures as modules. So it's again going back to this idea of modularity and structures that are modular, that can be reconfigured, that can be changed. So you can see these models that you can see here. One is SLS printed, laser sintered, and the other one is laser cut elements. They use identical modules as basic units, and also this example here. When was it? 2 years ago, 22, when I was yeah. So that was a few days of workshop in Navarra, based on some of these ideas, and I only picked one of the results. I didn't want to. Maybe it's already overloaded, but I didn't want to overload it more. So I think one of the most successful groups here. And these diagrams are also quite interesting, because if you look at the central image, The hyper is a doubly curved or doubly ruled surface, so that means you have two directions of lines. And maybe it's not so far away to think of that as something that could also be a woven structure. Maybe that can be some inspiration. Yeah, in the same kind of framework of modular hypers, last year we submitted this design for the ISS conference, International Association of Space and Shuttle and Spatial Structures. And so this is a realized structure that shows that these modular hypers can be realized from flat elements as well. So I showed earlier here, you can also see it here very well. This is the typical hyper that you can build from lines. And when I prepared that course, I came across some interesting geometric principles that actually you can place a diagonal grid on that, and then you can create these double curved surfaces from flat panels. We're coming to the final slide, which is this. Oh, sorry, it's not the final slide. But this is coming soon. It's a continuation of that, and hopefully this August it will be standing somewhere. I will close with some words of inspiration. I hope your brain is still open a bit. So when I did my PhD and studied all these textile principles, I also came across some textile creators from Bauhaus. So this was Annie Albers, and I just picked two quotes that I think are maybe interesting for you. So if you work with a specific material and with a specific technique, then try not, it's maybe not possible to force something upon this, but you have to kind of find a dialogue between what you want and what the material and the technique can do. So that's one. And then this also goes a bit back to the tectonics, what I talked about in the beginning. In textiles, it's really fascinating that you have this direct link between the appearance, how it looks, and the structure, how it's put together. So this is another quote from Annie Albers, where she says that sometimes material surface together with material structure are the main components of a work, and this can be the case in textile works, in weavings, or on another scale in works of architecture. And with this I come to the end of my presentation.